You've no doubt already met the Système International. It's important for industry as well as science. Just think of what things like GPS would be like if we didn't have an international standard to define the meter. In this course, we'll restrict our attention pretty much entirely to these three of the base SI units. If you go on and take Physics 1201, you'll meet electrical current, which we measure using the ampere. And no doubt in other courses you've already met moles and kelvins. You'll probably never meet the candela unless you do very specific work on light. Now, one thing to realize about measurements and about units is that all measurements are a comparison between the thing that you're measuring and some standard. And when you set your measuring instruments to work in terms of that standard, you call that calibration. And it's an experiment. So just read this little passage, pause the video for a moment, read this passage about how they defined the foot in 16th century Germany. So, if you were wondering what these guys on the front page were doing, that's what that's all about. Here is, perhaps this is a length of cloth or something, and it's stretched from the front of this guy's foot to the back of this guy's, and they're going to fold it in 16, and that will set the foot for perhaps that town that year, or however long they keep the standard. Well, we don't do it that way anymore. So the main purpose of SI is that it establishes the experiments which can be done to calibrate measurement instruments. And so, for example, there's our current definition of the second. It's to do with a particular transition in cesium-133, and you just count periods. That's a lot of periods, right? So you need very precise instruments to do this, and the thing you use is what's called an atomic clock. And the whole set of standards is updated every now and then to keep up with advances in technology, because, of course, as our technology improves, we can make measurements with more precision. And just be warned, there's a great big shake-up to the SI coming, probably in 2018, so it's all about to change. You've already done an activity in class about orders of magnitude. I'll just mention that usually you'll watch the video lectures first and then go to class prepared, but this is the beginning of term, so you're not quite into the pattern yet. We use scientific notation, which is a way of writing numbers in terms of orders of magnitude, because it's easy. You may not feel that it's easier, but just look at these two numbers. I could have written that number of periods of light this way. But then think, if you wanted to read it, you have to go and count digits to figure out that that 9 is in the billions place. Here you see that it's in the billions place, although I'll say scientists would rather say 10 to the 9 than billion, and part of the reason is, for example, that what we mean by the word billion in North America is different from what they mean by the word billion in, say, Britain. And I encourage you to watch these videos at some point. This one is kind of old. It is a little dated, but in many ways I think it's better than the more modern one. They're both pretty neat, though. You should already know these SI prefixes. These are the most commonly used ones. If you don't know them, learn them. That's it. So we only have 7 basic units, but they're enough. There are a lot more than 7 types of things that can be measured, but these 7 basic units are enough to build the units for all the other known measurable quantities. Maybe someday we'll find some other basic units that we need, but at the moment we know 7. So now the question is, how do you determine how the units of some new quantity that you've encountered are related to the base units? So let's do an example using these quantities. This is a velocity, an acceleration, and forces. So the way you determine what the units are of a quantity you've met that is unfamiliar is you just use any equation that can define the quantity. So you probably know the units for most of these, but let's just see how it works. So a V is a change in position, which is in meters, divided by a change in time, which is in seconds. So we can express a velocity in meters per second. You can now carry that on to the next one, an acceleration. Well, it's a delta v, a change in velocity, so that's meters per second, divided by, again, a delta t, so that's in seconds, and so that's meters per second squared. Finally, we can look at this one, a sum of forces. Well, a sum of forces is a force, and it's a mass times an acceleration. Well, a mass is in kilograms, and an acceleration we just found is in meters per second squared. And there we go. And you'll later learn, if you haven't already, that this is a Newton. Let's do a quick unit conversion. Hopefully you've seen this in other courses, but this is a refresher. So we have some flow rate, some stuff coming out of the end of a duct or pipe, and it must be pretty small because that's not very much. But let's convert that to cubic meters per hour. And all I've done so far is I've taken it and I've rewritten it so that it's clear that the units have a numerator and a denominator. And hopefully you've been taught that you need to use unit conversion fractions. This makes it a lot easier to just get this right. So I'm going to do the seconds first because they're easier. So these seconds are in the denominator, so I'll put seconds in the numerator of my conversion fraction so that those will cancel. And now we just have to say, oh, how many seconds are in an hour? In 1 hour there are 60 squared, or 3,600 seconds. And so that's been arranged so that the seconds are going to cancel out and we'll be left with hours. Now, milliliters. There are all kinds of ways you could do this milliliter to meter cube conversion. I'm going to take one particular path because I want to illustrate something. So you may or may not know that a milliliter is a cubic centimeter. And so I'm going to rewrite it that way. Milliliters I can just replace with cubic centimeters. And now here's where a lot of students make an error, because it's really tempting to say, oh, I know how to do that. 1 meter is 100 centimeters. There. Okay, but that's wrong, because there may be 100 centimeters in a meter, but there most certainly are not 100 cubic centimeters in a cubic meter. Think about it. If you take the little cubic centimeters and line them up across this front corner, you're going to this front edge, you're going to have 100 of them. And then you make more lines, and you end up with 100 lines before you've covered the bottom. So far you've got 100 squared, and now you need to stack up 100 of those layers. You end up with 1,000,000. The easy way to make this work is just to say, okay, I've got centimeters. I know how to convert centimeters to meters. Well, I just need to do it 3 times. I need to multiply by this conversion fraction 3 times to convert all 3 of those centimeters. And so we're done. I'm going to have my 40 times 3,600 divided by 100 cubed. And that'll be, the centimeters are all going to be gone, and I'll be left with cubic meters per hour. And you can now plug that into your calculator and you're done. So there's a difference between what we mean by units and what we mean by dimensions. And to illustrate it, let me just start off by asking these 2 questions. What's 3 miles plus 4 hours? And is it true that 5 kilometers equals 5 kilograms? Well, I hope you see that these are both total nonsense. You can't add distances and times. You can't equate masses and distances. Well, these are because they're in different dimensions. Now, you could add miles and kilometers. It doesn't matter that those are different units. You're allowed to add them, although to carry out the addition, you would have to convert one or the other. But there's no way to add miles and hours. So they have not only different units, but different dimensions. They're fundamentally different quantities. And you can think of a dimension as just a thing you measure in a particular way. So time is the thing we measure with a clock. Length is the thing we measure with a ruler. Now, of course, some lengths are so small that a ruler isn't a convenient thing to use, or so large that a ruler isn't convenient. But that doesn't change that it's the same quantity. So You've heard that you can't add apples and oranges. Well, you can't add kilometers and years. You can only add quantities of the same dimension. And the two sides of an equation have to have the same dimension. We can multiply and divide them. We've already done that, right? That's how we got that a speed is in meters per second, by dividing a length by a time. You can use this idea to check whether you've written equations correctly. And let's do that. And I'll just point out that constant numbers in equations are usually dimensionless, and that'll come up in the example I do. So sometimes you write down an equation and you're not sure you've remembered it correctly. So this is an attempt, an incorrect attempt, to write down an equation that we'll meet in a few classes when we're doing uniformly accelerated motion. And I've highlighted the different parts just so that as I do the dimensional analysis you can see what I'm up to and what is turning into what. So if you want to now check the dimensions of this, you just take it and you plug in the units for each quantity, right? So VF, that's a velocity, and we already know those are in meters per second, and that's squared. And now that equals, and now we have another velocity, meters per second, also squared. Now, that too is dimensionless, so we don't care. We can just leave it out of the dimensional analysis. It makes no contribution to the dimensions. This is an acceleration, and we've seen that an acceleration is meters per second squared, and there's a time, seconds. Okay, and so now if you just carry that all out, you've got meters squared per second squared equals meters squared per second squared. So far, so good, but now look, we've got meters per second, and meters per second are not the same units as meters squared per second squared. So now we know there's something wrong with this equation. It can't possibly be right. It's just like saying my age is 3 kilometers. And so you could now go about trying to fix it. There's just one more issue to deal with dimensional analysis, and it actually won't affect you much in this course, but you'll see it in other courses. And that's the issue of how transcendental functions work. Now, you might not be familiar with this term, transcendental functions, but here are a bunch of functions which are transcendental, and you've met these things. So these are just examples, and take a calculus course to find out what a transcendental function really is. But the main point is that the output, right? It's a function, you put a number in, it spits out a number, that's the output. The output has to be dimensionless. Also, the argument, the number you put in, has to be dimensionless. So here's an example. This is an equation that you would encounter in circuits. It's to do with the current in an RC circuit, and let's not get into that anymore. But this I is a current measured in amps. Now, you know then that this exponential over here has to be dimensionless. And so if the left side and right side are to have the same dimensions, then this I0 must also be a current. Then this t is a time, and since the argument of the exponential, all of this has to be dimensionless, for that to be dimensionless, RC must also be a time so that the times cancel out and you get a dimensionless number. And so even though all you knew was that this is a current, you can still come to lots of conclusions about the units that things must come out to.